All right, so let's just dive right in. When I say the word GPU or maybe Nvidia, what's the first thing that pops into your head?
For most people, it's going to be gaming.
Gaming, for sure. Or maybe Bitcoin mining. Or, if you're really following the latest tech, it's ChatGPT and AI.
Oh, absolutely. And for most people, those are the right answers. They're the powerhouses. But if you strip all that away, if you ask me what its fundamental job is, mathematically speaking,
Okay.
I'd give you an answer that, well, it surprises most people. It's Maxwell's equations.
Maxwell's equations. I mean, that is a complete shift in context. We're talking about fundamental physics.
We are.
The rules that govern electromagnetism, everything from, light to radio waves. So you're telling me that the piece of hardware that makes dragons look real in a video game is actually built to solve the physics of the universe?
In a very real sense, yes. Look, everyone sees the GPU as an accelerator for graphics or AI. But if you talk to the engineers, the ones actually designing the next generation of chips or antennas or radar systems, they'll tell you the GPU isn't some luxury.
It's essential.
It's the fundamental physics supercomputer they need to do their job. Without it, development it grinds to a halt.
So that's our mission for this deep dive then. We need to unpack that. Why your graphics card is really a physics engine, and maybe more importantly, this idea of a computational cost. Why simulating reality is so expensive that a normal computer, a CPU, just can't pay the bill anymore.
Exactly. And we're going to ground this in a problem that sounds simple but is incredibly complex. Simulating radio waves.
Yeah.
To really see how a signal moves, you need a level of precision that just breaks traditional computers.
Let's start right there with the problem of scale. The source material calls it a simulation nightmare, which sounds dramatic.
It is. Imagine you need to model how a Wi-Fi signal, a really high-frequency one, moves through, say, this room.
An office or inside a car, something complex.
To do it right, you have to use a specific method based on Maxwell's equations. The core idea is that you need a 3D grid. You can't just talk about the wave in the abstract. You have to discretize the space.
You mean chop it up into little pieces?
Exactly. Think of it like a microscopic Minecraft world. You cut the entire room, the antenna, the circuit board, everything, into a massive stack of tiny, invisible cubes.
And this isn't for visuals, this is for physics, for
So
accuracy.
Precisely. Because when you solve these equations, you're not tracking a single point. You're calculating fields. You're
Yeah.
calculating how the electricity in one tiny cube affects the magnetism in the cube next to it, and how that all changes in the next tiny fraction of a second.
And for that to work, the cubes have to be really, really small.
They have to be a fraction of the wavelength. So if you're simulating something like future 6G technology, the frequencies are incredibly high, which means the wavelengths are tiny.
So the cubes have to be minuscule.
Right, and the numbers get crazy fast. Let's say you're simulating a small structure, maybe 5 meters wide. Not a whole building, just a small area. To get the detail you need, you are very quickly looking at needing 1 billion of those little cubes.
A billion. And that's just to represent the empty space before anything even happens.
That's just the starting point. Now, here's the part that breaks everything. For every single nanosecond or even femtosecond that passes in your simulation, your computer has to do an update.
An update.
It has to calculate both the electric field vector and the magnetic field vector for every single one of those billion blocks. It's this huge, continuous, and very repetitive task.
Okay, so that sets up the problem. A billion blocks, constant, simple math. Let's talk about the CPU, the central processing unit. Why does the brain of the computer, the part that runs everything else, just completely fail at this?
Well, we often use the analogy of the CPU as a genius math professor.
Yeah.
And it's a good one. It's brilliant. It can handle incredibly complex single-threaded problems better than anything. But the key word there is sequential.
It does one thing, then the next thing, then the next.
It takes the problems in a line, exactly. So if you give it a billion cubes to update, it has to, load the data for cube 1, do the math, save the result, then load the data for cube 2, do the math, save the result, on and on, a billion times.
The overhead must be insane.
It's not just inefficient, it's fundamentally broken for this kind of work. It's like asking that one professor to grade a billion simple math problems in an hour. They'd spend more time shuffling the papers than actually grading. The system just chokes. The time it would take is it's useless for any real engineering work.
So the CPU is almost too smart for the job. Its strength, that deep sequential thinking, is its biggest weakness here.
It is. It's a volume problem. And you can't solve a volume problem by just being a little bit faster at doing one thing at a time. You need a totally different architecture.
Which means you can't solve these billion problems one after another.
You have to solve them all at once.
And that brings us, of course, to the GPU. The graphics card, designed to draw millions of pixels on a screen at the same time, now gets pulled into the world of physics.
Right, so if the CPU is our one genius professor, how should we think about the GPU?
I'm waiting for the analogy.
The GPU is an army. It's an army of, say, 10,000 elementary school students.
10,000 elementary school student. Okay, I'm trying to follow this. That sounds like you're sacrificing quality for quantity. Doesn't the CPU's smarts, its complexity, matter at all here?
It matters for controlling the whole simulation, for setting it up. But for the core work, the actual grind, no. The math inside each of those billion cubes is simple. It's addition, multiplication, moving data around. It's arithmetic.
That doesn't need a genius?
It doesn't need complex logic.
Yeah.
What it needs is massive repetition. And that's what a GPU is. It's thousands of simple cores that are all designed to do the exact same simple thing at the exact same time.
So you give the same simple instructions to all 10,000 students at once.
That is parallel processing. We call that little set of instructions a kernel. You design a kernel for the physics, you load it onto every core, and you give each core its own little chunk of the billion-block room to manage, and then they all press go in perfect sync.
Cheating the clock by doing millions of calculations at the same time instead of in a line?
And this is where you see the practical application. You take simulation code that was written for a CPU, maybe in a language like C, and you rewrite it for the GPU using a framework like CUDA. You have to think differently, structure the data differently, but the result is, well,
The result is a massive speed up. I mean, what are we talking about here? What's the hard number?
for these kinds of simulations, these Maxwell's equation solvers, we have seen them run 500 times faster.
500.
Let me make that real for you. I've watched PhD students set up a simulation on a really powerful server and have to wait an entire week for it to finish. One run.
A whole week.
Now, with a decent GPU, that same simulation finishes in 20 minutes.
From a week to 20 minutes. That's not just an improvement, that changes what's possible. An engineer can now run dozens of different designs in a single day.
Exactly. It changes the entire design philosophy. If a test takes a week, you're going to be very conservative. You run one, maybe two tests. It takes 20 minutes. You can try 100 variations. You can optimize for things that were just computationally too expensive to even consider before.
And that aggressive optimization, that ability to test everything, that leads directly into this fascinating loop you mentioned, the self-fulfilling loop.
It does.
The idea that the chips are basically designing their own successors. How does that actually work?
It's this incredible and really unavoidable circular process. We're using the GPUs we have today, the ones that are great for gaming and AI, to solve the physics of electromagnetism in a way we never could before.
Okay.
The data we get from those simulations, the super precise field calculations, the signal interference maps, the heat models, that data becomes the blueprint for the next generation of hardware.
So give me a specific example. Where does this GPU-powered physics simulation actually inform an engineering decision?
Oh, everywhere. Think about the machines that make the chips, the lithography machines. They use extremely precise light to etch circuits onto silicon. Designing the optics for that, the lenses and mirrors, requires solving Maxwell's equations for light with insane precision.
And you need GPUs to run those light simulations.
Without them, you can't design the new lithography system you need to make the next generation of smaller, faster transistors. It's a direct link.
So that's the manufacturing. What about inside the chip itself?
Same thing. You have signals flying around a circuit board at incredible speeds. If the timing is off by a tiny fraction, or if two signals interfere with each other, the whole chip fails. We use GPUs to simulate all that electromagnetic chaos and perfect the design before we ever make one. We even use them to simulate airflow and heat to design better cooling systems.
So the GPU is simulating the heat, the light, the signals, all to make the next better GPU possible. It's an engine of innovation that just keeps feeding itself.
That's the beautiful irony of it. And you see it clearly with wireless tech. The super complex antennas we need for 6G, they simply could not be designed without the simulation power of the GPUs that were originally built to help develop 5G.
The current generation is the absolute prerequisite for the next one.
It is.
So the next time you see a GPU in a gaming PC or you hear about an AI data center, you have to remember this. That same architecture, that army of simple processors, is what's fundamentally designing our future. The phones, the networks, the computers, all of it.
And if you're an engineer or just curious and you want to go deeper, the source material actually walks you through it. It gets into the details of how you allocate those huge 3D arrays in memory and how you actually write the CUDA kernel that lets a graphics card do this kind of magic.
A great next step for anyone who really wants to get their hands dirty with this stuff.
But if we just zoom out one last time, think about what this means. This loop, this constant acceleration of chips, designing better chips by solving physics. It's literally setting the speed limit for human innovation.
The pace at which we can understand and manipulate the physical world is now directly tied to our computational power.
It is. The speed of physics is now tied to the speed of silicon.
That is a very powerful thought to end on. Thank you, as always, for this.
My pleasure.
Incredibly insightful. Thank you for this deep dive.